Okay, so 9.9 is the area bounded by two polar curves. So remember, yesterday we did 9.8, which is area bounded by one polar curve. And so once we found when r was equal to 0, found those theta values, those became our bounds. Now we have two functions. So not only are we going to be paying attention to when r is 0, but we're also looking at the intersections. So the first part says, recall the area bounded by a polar curve is a is equal to 1/2 integral alpha to beta r squared d theta. So the same formula from yesterday. It says things to watch out for since we're looking at more than one polar curve is the point of intersection, because that point of intersection is most likely going to be one of our bounds. And then the symmetry part Sorry, say that again? You're more than welcome to look. Okay. Okay, and then the symmetry part, if we are looking at the curves and they are symmetric, that means we can actually just solve for half of the area and then double it. Okay, so it helps us out, makes it a little easier. So I'm just going to write, this is used for the bounds. And we can find half the area. And then, of course, double it to find the entire area. So number 1 says find the area of the region common to the polar curve r is equal to 4 cosine theta and r is equal to 2 sine theta. So since they did not give us a graph, that is our first step, is to graph it. So on Desmos, I'm just going to type in those exact equations. So r is equal to 4 cosine theta, and then also just double check that it's in radians. And then r is equal to 2 sine theta. And then what we have here is our image of the two polar curves. So I'm going to go ahead and draw that on the notes. Okay, rough sketch, doesn't need to be perfect. As long as we are seeing the intersection. Okay, so the blue circle is the smaller one, that is sine. So I'm just going to color code it like it has here. And then the red one is cosine. And what we are trying to find is this intersection here. Okay, so where the two polar curves overlap. So in order to do that, the very first thing we do after we graph everything is we need to set these two polar curves equal to each other to find what theta is equal to. So we have 4 cosine of theta is equal to 2 sine of theta. So if you use the insult feature on Desmos, you can use Desmos, just replace the equal sign with a tilde or that squiggle. So 4 cosine theta, then equal to 2 sine theta. Remember, if you accidentally put equal, it's just going to pop up an error. You're not going to get an answer. So just make sure you use that little tilde because it puts it into a regression, and that's what helps us solve. So the intersection here, and what you notice, if you try to click on Desmos, it's not going to tell you the intersection like it does on other graphs. You're not able to click and find that intersection. So what we end up getting is 1.10715. So I'm just going to say theta is equal to 1.107. So again, that is the intersection, and that is this exact intersection here. Okay. Now the next thing that we need to do is we need to take each of these equations and let r equal 0 so we can find each of those theta separately. So I have 0 is equal to 4 cosine theta. This means that theta is equal to pi halves. When you do this on Desmos, it's not going to put it in terms of pi. So I know it's pi halves because it gave me like 1.5 something, and if you want to compare it on here, so let me just show you real quick. So 0 is equal to 4 and then cosine theta. See here it gives you that 1.5708. On the next line, if I put pi divided by 2, it's the same thing. Okay, so just know if it might give you the decimal, which is fine. You can use the decimal instead of it being in terms of pi. Okay, and then the next one, setting the other one equal to 0. So 0 is equal to sine of theta. And then since this is sine of 0 when theta equals 0. Okay, so really what we did is we found this part here. Okay, because this is 0. Okay, and we also found this part here because this is pi halves. Okay, and then this is the intersection. So in order to set this up, we are going to do the same formula for integration, but we're going to end up adding both of these polar curves together. So we're going to do the integral of one with the correct bounds and then add it to the integral of the next. Okay. So we have area is equal to 1/2, so I'm following the formula. Integration from, notice 0 was our smaller bound, okay, and we're going to look at sine, which is the smaller circle. Okay, so when we solved for theta on sine, we got 0, and then we know that it intersects at 1.107. Okay, and then it's r squared, so this is going to be 2 sine theta squared d theta. And then we're going to add 1/2 integral, and we're always going to start where we ended on the last integral. So since we ended at 1.107, which was the intersection, I'm going to write that value. And then when we set the cosine function equal to 0, we got pi halves. So pi halves is the other bound. And then this is 4 cosine theta squared d theta. Okay, so you would type that entire thing into Desmos and it would give you your answer. Okay, you are not required to solve this by hand at all on the entirety of 9.8 or 9.9. And so when you solve it, you get that the area is equal to 0.9617. Okay, yes?
So why do we have the second integral going from 1.107 to pi halves?
Because we're looking at the cosine portion where it overlaps. So we are looking at where it intersects here, and then pi halves is going to be when we set this one equal to 0. Okay, and know that each part of this is in terms of pi halves. Remember, it starts at 0, pi halves, 2 pi halves, 3 pi halves. Okay, so because this got set equal to 0 and got pi halves, that has to be our other bound with this equation. So what we're really doing is we are taking one polar curve, doing the integration where the bounds are surrounding that area, and then we're adding the integration of the other curve, only the bounds surrounding that area.
Okay.
Okay, and again, we find those bounds by either setting it equal to 0 or setting them equal to each other. Always. Okay. So for the rest of these, we still need Desmos, but I'm just going to write the answer down for each of the thetas that we find in area, just so I can have a larger screen here. but you're more than welcome to keep following along on Desmos. Okay, so now it says find the area of the common region to the polar graphs of r equals 2 and r equals 2 minus 2 sine theta. So r equals 2, that is this circle here that has a radius of 2. And then the other one, 2 minus 2 sine theta, is this one here. Okay, so what we need to find is the overlap. Okay, so that is this section here. Notice, however, that both of these polar graphs are symmetric around the y-axis. Okay, meaning I can directly divide this in half and it will be even on both sides. Because of that, this is where we use the property of symmetry, and I'm actually only going to find the area of just half of this. Notice I picked the positive half just to make it easier. Okay, which means when I'm finding the area, after I find this area here that I highlighted in yellow, I'm going to have to take my entire answer and multiply by 2. Okay, so again, first step is to find our bounds by setting these two equal to each other. Okay, so I have 2 is equal to 2 minus 2 sine theta. Solve that on Desmos and you get pi halves. Okay, that makes sense because look, this is where it is equal to 0 on this line here. This whole line is pi halves. Pi halves positive on the top, negative pi halves on the bottom. Okay, so this is pi halves. The other thing I need to pay attention to is this section here. So since I'm only paying attention to the positive part, notice how it's crossing right here. If we're starting here, we would consider this 0. Okay, so we're going to have the intersection of 0. So let me right here. This intersection of 0. Okay. And we are going to have that it both are symmetric on that line that is pi halves. Okay. So since I'm looking at only half of it, this is telling us that half the area is going to be equal to 1/2 integral. And since we just said this is symmetric, that means this one on here is negative pi halves. Okay. And so what I'm going to pay attention to is I'm going to pay attention to the bottom of this shaded region, which is being outlined by the blue circle. So r is equal to 2. And so since the bottom of this is at negative pi halves, I'm going to go from negative pi halves to 0. That would be my first one. Okay, of r squared, so that is 2 squared d theta. Again, that is the bottom of that shaded area where they overlap. Plus 1/2 integral, and I'm always going to start where I ended. So I ended at 0, and then I'm going to go up to the positive pi halves. Okay, and notice now that I'm at the top. So I started here, and I'm going now to positive pi halves. Now the green function, okay, so the 2 minus 2 sine of theta is on top of the shaded area. So that's what I'm using next. So it's almost when we were doing the area between two regular curves on the rectangular plane. Okay, we're still looking at the bounds that are going to encompass that shaded area. So when I do this and I type this into Desmos, I end up getting that 1/2 the area is equal to 3.8539. That is just that yellow shaded region. I have to double it to find the entire shaded region, and I get areas equal to 7.7079. So this is another section of notes where it would be extremely helpful to know your unit circle. Okay, extremely helpful, especially just the quadrants, like how it goes from 0 to pi halves, 2 pi halves, 3 pi halves, etc. Okay, any questions on 1 or 2? Okay. Number 3 says find the area of the region common to the two polar curves. And so we have r is equal to -6 cosine theta. Okay, so that is the normal large circle here. And then the other one, 2 minus 2 cosine theta, is this one here. Okay, so it wants us to calculate where they overlap. So this is where they overlap. Okay, however, what do you notice about these polar curves? Good, they're symmetric across the x-axis this time. Okay, so that means I can look at just this section, okay, find the area of what I just shaded in yellow, and then double it to find both areas. And that's because, again, both of these curves are symmetric over the x-axis. Very important that they both need to be, not just one. Okay. So then the first thing I'm going to do is I'm going to set these two equal to each other. Remember, you do that on Desmos to find theta. So I have -6 cosine theta is equal to 2 minus 2 cosine theta. Okay, again, you do that on Desmos, and you're going to get some decimal that it represents 2 pi thirds. I can't remember what it is, but it is going to represent 2 pi thirds. Okay. Then I am going to set the r equals -6 cosine theta. Let r equal 0 here and find theta. So 0 is equal to -6 cosine theta. Again, you plug that into Desmos. You get theta is equal to pi halves. So if we're looking at this, again, only that yellow shaded region, we have the 2 pi thirds where they intersect, so that's right here. Okay, we have the pi halves or negative pi halves, so that would be where did I put it on? Should be right. It should be up at the top somewhere. Oh yes, okay, never mind. Sorry, I'm looking at the wrong thing. It's right here because this is the y-axis. That's what I was looking for. This is the y-axis, so you know that whole line is pi halves or negative pi halves on either side of the unit circle. Okay. So then from here, we're going to find that area. So it's going to be 1/2 area is equal to 1/2 times the integration of, and we're going to start with cosine or -6 cosine of theta, because if we're looking at this, since it's turned off to the side, that is on the right. Okay, so again, looking at this part, we're looking at the right side, which is surrounded by the purple line, so that's that -6 cosine theta. And so for that one, we got pi halves when we set it equal to 0, and then when they intersect, so here's pi halves, and then when we set them both equal to each other, that's 2 pi thirds. Okay, so that's the bounds for the first one. So pi halves, 2 pi thirds of -6 cosine theta squared d theta. Okay, so now I have to do the left side, and that is going to be the green polar curve, so the 2 minus 2 cosine theta. And so I'm still going to start right here at 2 pi thirds. That's where I ended my last one. And I think I forgot to put the 1/2. So it's always 1/2 because we're following the area formula from above. Okay. So now we're looking at only this section here. So this is the 2 pi thirds, okay? And then we need to go to this point right here, okay? This is where we can get confused, and most people will say, well, this is 0, okay? But it's not going to be 0. 0 wouldn't make sense because that would mean we would have our larger bound on the bottom, okay? Another way that we can say is 0, because we're talking about this line right here. Yes, it's 0 where we start, but when we end, what is it? Pi. Okay, so this is saying this is, let me write it out, this is 0. We go through the entire unit circle, and we end at pi. So remember, 0 and pi can be exchanged. We don't want to do 0 because it would make an improper integral. So then I write pi, and then we're using the 2 minus 2 cosine theta squared d theta, and then we have everything set up. Okay, so if you were to plug this into Desmos and then take your answer and multiply it by 2, because we only got half of the area, we would get area is equal to 15.7079. So again, on your own time, double check that when you plug this into Desmos, you get the same thing. Just that tells you that you are using Desmos correctly. Okay, any questions on 3? Okay, so the next part of these notes is saying area bounded by the 2 polar curves. So it's saying, what if there is a gap in the section that you're trying to find the area of, and you do not want a certain piece of the graph to be in there? Okay, so let's say this whole entire section we are given to find the area, but really we only want this part of the area. Okay, so this brings us to when we talked about the area between 2 curves, and what we were doing is we were taking the area of one and subtracting the area of the other to find out what was left over. Okay, and so when we do that for polar curves, we're always going to look at the one that is on the inside, okay, and we call that R1. Okay, so the polar curve on the inside. And by inside, I mean closest to the origin. And then R2 is the one on the outside. Okay, so just like we did on the different notes when we were in the rectangular plane, we took the 2 graphs, we subtracted them to find what was left over. We're doing the same thing here. So this becomes 1/2 integral of alpha to beta R2 squared d theta minus 1/2 integral of alpha to beta of R1 squared d theta. Okay, notice we're using the exact same bounds. Okay, because we're going to be looking at subtracting the 2 areas, so we only have the part that's left over. Okay, just like before, we always use those same bounds. So because they are the same bounds, I can combine this into one integral, and this can be written as 1/2 integral alpha to beta of R2 squared minus R1 squared d theta. Okay, so we're taking the polar curve on the outside, subtracting the polar curve that is on the inside, squaring each of those, and then integrating from our alpha to beta, our bounds. Okay, so this is actually a lot easier than the first couple we were doing because it does relate to what we've done in a previous unit. So number 4 says find the area of the region bounded by the 2 polar curves, r is equal to 1 and r is equal to 1 minus cosine theta as shown in the graph below. So first, just color coding them. Here is r equals 1. That is a circle with a radius of 1. And then we have the other one, 1 minus cosine theta. Okay, it wants us to find this shaded region here. But what do we notice about these two polar curves? They're symmetric. So they're symmetric across the x-axis, which means just like before, we can still use those rules of symmetry and only find part of the area and then multiply it by 2 later. Okay, so I am only going to find this top positive portion. You can barely see that. Let me highlight. There we go. Okay. So first thing I'm going to do to find my bounds is I'm going to set the equations equal to each other. So again, you would do this on Desmos. So 1 is equal to 1 minus cosine theta. This gives me that theta is equal to pi halves. Okay, that is this intersection here. Okay. And then since we are going to be starting, okay, and going this way, that starting value right there on the unit circle would be 0. Okay, which means we are using the bound 0 to pi halves. Okay. So then writing out my equation, I'm finding half of the area, and that is equal to 1/2 integral from 0 to pi halves. Okay, and then I have to determine which one is my function that is on the outside. Okay, remember it's going to be the outside function minus the inside function. So looking at just this part that I shaded, which one is on the outside? Good, the green one. R is equal to 1. So I'm going to do 1 squared minus the other one. 1 minus cosine theta squared d theta. That's the hardest part. It's determining, make sure you're doing the correct outside function minus inside function always. Okay. And so when you solve this, you'll get half the area. You take that value, you multiply it by 2, and you get area is equal to 1.2146. Okay. So one other thing I want to add, that ends the notes, but one other thing I want to add is, let's say we forgot about that property of symmetry. Okay, and let's say we looked at this entire function here. Okay, that means we would have this bound, which is what? Negative pi halves. We're just, you're right, but I'm trying to show something, but yes, that is correct. But negative pi over 2, because it is symmetric. Okay, so if I was to do the integral from negative pi halves to pi halves, what would happen?
It would be 0.
It would be 0, right? Because I would be saying I have a positive area and a negative area, that would be 0, which is not true. Okay, because we clearly see a shaded region here. Which means if you're choosing to skip the symmetric portion of it, you would have to split this into 2 integrals. You would have to do the negative pi halves to 0, and then 0 to pi halves, and then add those 2 areas together. That's more work. Might as well remember the symmetry part. And once you find one of them, and notice how we always pick the positive one, easier. Okay, and then when you multiply it by 2, it gives the entire thing. So that's one thing to keep in mind, that if you do decide to use the entire bounds, okay, most cases, because if they're symmetric, especially like this, symmetric over the x-axis, you're going to get a positive area and a negative area that cancel out to 0.